Hi, everyone. We would like to welcome you all to this talk of the IEEE GRSS-APS-SSCS student chapter at the University of Southern California. Today, we are pleased and honored to have this talk presented by Dr. Babak Vakili-Amini, entitled Ultra-Wideband Technology, New Era, New Use Cases. Dr. Babak Vakili-Amini received the BS and MS degrees in electrical engineering from the Iran University of Science and Technology in 1996 and 1998, respectively, and the PhD degree in electrical and computer engineering from the Georgia Institute of Technology in 2006. From 2006 to 2011, he worked as an analog RFIC design engineer at Atheros Communications. From 2011 to 2016, he was part of the connectivity group at Qualcomm, working on the cutting-edge radio communication design for Wi-Fi, Bluetooth, and BLE. From 2016 to 2019, he was with the SpaceX Starlink project, where he was leading the radio design for the digital beamformers in Ka and Ku bands for the satellite internet. Since 2019, he has been with NXP Semiconductors, where he is the director of analog RF engineering, engaging in the design and development of integrated CMOS transceivers for UWB communications. Dr. Vakili-Amini, we would like to welcome you again, and the floor is yours.
Thank you, Michelle. I appreciate that. And thanks, everyone, for joining us. I'm sure many of you guys, like myself, had a long day, either at work or school. So let's make the presentation a bit of a fun, so we can eventually learn something from each other. I think there will be some time at the end for question and answers, so we will wait for that. If there are any questions that I can't answer, good news is that I have a lot of capable colleagues to go back and ask and bring the answer to the question later. So let's get started. Let me minimize in my side. So here is the outline of the talk. This presentation is based on a 2022 RFIC workshop that I did with the same title. And all the material that are presented are public domain material, so they're publicly available. You should be even able to get a copy of that RFIC workshop. No, it should be available. So I start with briefly talking about the UWB, especially the impulse radio version of it. Talk about the ranging techniques. There are multiple ways of measuring the distance and locationing, so I will talk about it. We look at the use cases, and towards the end, I have some radio block examples that we'll get there. My plan is to mainly give you the big picture, kind of as we walk through different aspects of technology. I would like you guys to think about what problems we have to solve when it comes to the circuit or RF or radio design. So from that perspective, you can kind of connect what the application wants to achieve versus what we have to deal with. And I have some slides to create that bridge as we work through. All right, so a brief discussion on what the impulse radio UWB technology is about. So it is a radio technology that has a pretty wide band signal coverage. It's let's say 500 megahertz up to 1 gigahertz. The carrier frequency is pretty wide. Again, the name brings that to the picture. So 3.1 to 10 gigahertz. It's very robust in detecting first pass weak wanted signal, and I explain what that means. Specifically when there's strong reflections or blockers. The interesting part about this technology is that it can have a very short frames, up to let's say 100 microseconds of pulses, and that brings the low energy consumption aspect of it. It uses pulse positioning or and polarity modulation, burst position. So it's called burst position modulation and binary phase shift keying. And there are some requirements from the regulatory aspect in different parts of the world that we have to respect. One of them is the average transmit power. The key is that either in band or out of band, it should be below minus 41.3 dBm per 1 megahertz measured over 1 millisecond EIRP. EIRP stands for equivalent isotropic radio power. And then there's a peak transmitted power limitation as well, which is 0 dBm or 550 megahertz of measurements. So then the key point is that unlike the ISM or unlicensed band, that they only have to respect the out-of-band requirement for their EIRP limit. For UWB, we have to respect that for our own in-band as well. So, for example, Wi-Fi or Bluetooth, they can blast the power up to, let's say, 20 to 25 dBm in band, as long as they make sure that out of band, they stay below minus 41.3 dBm per megahertz bandwidth, they are fine. But UWB, due to the fact that it's supposed to be, almost noise-looking radio transmitter and receiver, we have to respect that in band as well. So you can see from that perspective, there's a lot of pressure to close the link budget based on the sensitivity requirements, distance, and the amount of power that we have to transmit. To the right, you can see the progression of the standard. You might even remember around mid-2000, there was almost a competition among Wi-Fi, WiMAX, and multi-band OFDM UWB, which is mainly database, not necessarily like this new way of looking at this technology. At that time, OFDM, multi-band OFDM tried to have a very high data rate, kind of replacing, kind of competing with Bluetooth and eventually Wi-Fi, but we know that they, at the end, Wi-Fi and Bluetooth were the winner of that field from the data perspective. But impulse radio is not necessarily getting to that route, and there are some data capability as well, as you can see here, based on very most updated 15.4 Z updates that came to the standard. You can go as high as 27.2 megabit per second, but this particular radio technology is used for ranging and indoor locationing and such. Usual frequencies that you see most of the companies kind of looking into it is based on this table here, which is channel 5, 6, 8, 9, 10, and 12. If we think about like 500 megahertz bands. All right, so let's move on. All right, so like any other technologies or radio technologies that we discuss or we deal with, there should be some sort of consortiums that they take the standard requirements and they try to make it workable for the companies and for the society. For example, we have Wi-Fi Alliance for covering the Wi-Fi requirements of Bluetooth SIG and Connectivity Standard Alliance for Zigbee and such. Similar to that, there's this consortium called FIRA or Finding Rangy or FIRA. It was formed in 2019. Main goal of it is basically what is shown here, kind of establishing an ecosystem of the devices and companies that they do UWB connectivity, chip design, obviously creating opportunity by identifying and developing use cases based on a standard, which is 15.4Z, to ensure that there is interoperability and different chips and different companies, products, they can talk to each other and all. That whole effort falls under this particular consortium, which is called FIRA. UWB is actually getting a lot of attention in automotive as well. And as part of it, there's this CCC or cross-industry organization that they oversee requirements of connectivity in the car. And they're also looking into applying the UWB for car access and such. And NXP specifically is part of that group. They kind of started their sponsor, a member of that consortium. All right, so let's give a perspective. The representation of UWB technology as a standardized secure ranging is still in its very earliest stages, assuming the use cases are literally popping up in different, different sectors of industry or consumer electronics. Due to broadly shared bandwidth, as we discussed, between UWB and other Wi-Fi technology, UWB communication must be robust to different blocker scenarios in RX and stay incompatible with different stringent emission mask requirements in TX that different regional regulatory bodies like FCC, HC, ARIP, and such define. They usually have their own mask requirements when it comes to regulatory limits, and that's where the challenges in TX design comes into the picture. And obviously in the RX side, blockers are the challenge. So this makes the radio design challenging, especially in the mobile platform when there are multi-radio technology can operate simultaneously, and therefore system level solutions are needed to augment the radio performance. For example, chance impulse response, also known as delay power spectrum, represents a multipass propagation behavior that is understood as a result of energy received by the receiver and plotted over time. And this results in a large processing gain and improved receiver sensitivity. As you see later in some of the practical SOC, published SOC solutions, we can gain a lot of processing by even having negative SNR, system level SNR. So SNR can be minus 10, minus 15 dB or minus 13 dB. And we gain a lot based on that. All right, so let's just go over some of the big pictures of the ranging techniques, and this should give an overall view of like what we can achieve by using UWB in the form of impulse response. So these are very kind of a standard way of measuring the distance. Ranging essentially means this distance or speed measurement. So they are based on time of flight. We know that electromagnetic waves travel at the speed of light. So if you have the time measurement, it means distance measurement because it's just multiplied by the speed of light and gives you distance. And that's essentially what we are trying to do. But there are different ways of doing it. For example, in this scenario, which is called single-sided two-way ranging, the green device here, which is initiator, sends a pole to the responder, and responder at the end responds back. And this initiator is just keep track of time. So it knows exactly when it transmitted the pulses, and it knows exactly when it received the pulses. The responder replies with the amount of the processing time that itself included in creating the CIRs and detecting the packets and such. And by putting that back in the response of itself, a very simple question here can give us time of flight. And that time of flight eventually gets multiplied by a speed of light and gives the distance. We can make it double-sided, which means that two ranging sessions can happen back to back. So initiators does a ranging and responder also does a ranging. The nice thing about this is that if there's any drift between the timekeeping mechanism of these two chips, which is really crystal drift, essentially it gets to the first order, it gets canceled. I mean, there's this reference that goes through the math and prove that, in the first order, any ambiguity in the time measurements of these two responder and initiator and responder can be canceled out. But obviously we have to have more airtime, which means power. So we basically have to burn more power to gain that extra accuracy in our distance measurement. This ranging sessions usually happen about 2 milliseconds. So the whole ranging, you can imagine within 2 milliseconds, it gets resolved. And obviously during this process, there are a lot of impulse radio pulses gets transmitted and received to do the packet decoding and eventually creating the CIRs. I will explain what the CIR means maybe in this slide. So time difference of arrival is another way of measuring or basically finding the location. And you will see in one of the slides that I talk about the use cases and application, why we do it and how we can leverage from it. But very simple example is in indoor, let's say within the malls that people are walking around, going to the different shops. By getting close to the shops, you can have very focused, dedicated advertisement associated to that particular shop. They might have special items or some sales going on that they can target each user based on they get close to that. In this particular time difference of arrival measurement, the initiator, which is let's say a user's cell phone, it's literally one directional transmission or connection. So it starts sending out the package, which is called blinks. And there are very specific fixed anchors within the infrastructure of the, let's say that mall as an example, that they measure the time of arrival based on their response to these received pulses. And since they know exactly where they're located and they are in a network, at the higher level, they are part of a network and part of a software solution to communicate to each other, they can, with 4 of them, we can very accurately find the location of this moving object. So they call it a 3D localization of that particular object. And you can see like if receiver number A4 is closer to the target, it gets the pulses faster than the A1 that is further away. And based on all these measured time and their own location, they can identify exactly where this this device is locating. Without really having any privacy problem, there's no video or visualization of target. It is just based on electromagnetic waves. It can locate that target. So by CIR I was talking about CIR is channel impulse response in time domain, would be a pulse that looks like this with all the carrier frequency that sits within it. When it gets down converted in the baseband filter and goes through the ADC, eventually you have this red pulse, and this red pulse gets averaged up with thousands and thousands of pulses that get transmitted, and you gain a lot of processing gain by just putting these pulses on top. The interesting thing is that these pulses are completely aligned with the distance from where these pulses are coming. So the shortest distance is actually the line of sight distance, so this like a straightforward distance. And that always shows itself as a first pulse in the CIRs, and every other reflected pulses will be after that. So that's another way of filtering, time domain filtering. Or you can even transfer this to frequency domain using FFT and do some post-processing in digital part of the chip to exactly find the peak of the CIR, and based on that measure the time and such. So another interesting use case of UWB's angle of arrival, kind of very basic concept of beamforming. Beamforming is really only one of, so this is really one, only 2 receivers to do beamforming, but beamforming usually involves with a lot of receivers. But the concept from the mathematical perspective is the same. You have 1 transmitter and 2 receivers that are separated, let's say, with a distance that is close to lambda over 2 and such. And you do basically two ranging. So when you send the transmit signal, the receivers receive that responder's response or responder signal at two different times, simply because they're physically located at two different points of, let's say, cell phone. One of them gets the signal faster than the other one. And assuming that this separation of the two antenna is much less than location of the responder, you can assume these lines are in parallel, and then a very simple equation can give you, the angle, like this theta, that this responder is responding to us. So that's another very interesting use case, but obviously you have to have at least two. There are cases that you can even give some depth to it, so you can have three receivers and create like 3D, create 3D version of this. Basically, you have a depth exactly where in the space that you're looking at the responder, you can exactly locate the responder. All right, so another one, which I think is the last one in my list of use cases, is radar. Impulse radio, UWB actually does radar as well. It's not like the car radar. Car radar is different. They use frequency, so it's called FMCW, or frequency modulation continuous wave, which is based on the chirp and all. For IR UWB radar, we literally look at the Doppler effect when the target is moving. If the target is not moving, so radar means detecting passive objects, the objects that they do not respond to our transmitted signal. All their response is based on our own signal that gets reflected based on the distance that they are. And obviously the delay associated to the response time, again, gets multiplied by speed of light and gets the distance, right? And if the object is moving, then there's this Doppler phenomenon that basically changes or modulates the carrier frequency of the return signal positively or negatively, depends on the target moving away from us or getting close to us. So that is another very interesting use case of UWB these days. And obviously, you can create, once you have this capability, you can create a lot of use cases, like gesture recognition, or application within medical use cases and such. And there are some very predictable equations with respect to what would be the resolution of the measurement when it comes to the radar and ranging as well. All right, so let me go over, just do a quick time check. All right, so let me go over through some of the use cases that is getting getting a lot of attention based on UWB technology. So the titles are shown here, like a smart city and mobility, smart building and industrial, smart retail, smart home, and consumer. Obviously, I don't want to go across across all of them, but maybe some of the use cases in, let's say, a smart city and mobility, like indoor navigation, vehicle, digital key, or access into the car using UWB, based on the distance, getting close to the car and such. There are a lot of them. You can, and this is available online in this reference 10, so you can kind of get familiar yourself with all these different use cases that are coming along. This particular one is very interesting, point and trigger. So basically, if you want to do, I don't know, money transaction, and instead of like, I think there are different ways of doing it, especially in China. They use a QR code and such, but you can do that using UWB as well. But all of these needs a lot of infrastructure and a lot of providers behind the scene, right? The technology exists, the chip exists, the security exists, but then let's say it is banking system or retailing system that they come and buy this technology to basically enable it for the consumers. This is one example of how the secure access how it works. The BLE, so let's say in the cell phone, you have UWB chip. As of today, a lot of iPhones and Samsung mobile, if you haven't heard of it, but there is UWB available in iPhone and Samsung, I think as of 2020 for sure. So what happens is that, let's say you want to get access to the house or to the car, and really car, what do they got? The door access, right? So BLE is the main host, that is as of today. BLE basically does the backup mechanism because it has the connectivity to the outside world as a standard. At the application level, it comes and picks up the UWB, and then from that point on, UWB takes over and does the ranging and security dispatching, and based on that, decides if the door has to be opened or not. NXP is obviously a provider of UWB chip from the very beginning when this came along as this new way of looking at ranging. We have a bunch of different chipsets that are available in our website, and you can see that they're stacked based on the kind of software stack. They can be either FIRA compatible or CCC compatible because each of them come with different requirements. So at the hardware level, we can support different protocol requirements based on the whatever product we're targeting. All right, so let me get to the some of the radio block examples that it comes with the UWB technology. I specifically picked these three papers. They are obviously available, ISSCC, all of them. I think maybe they have some follow-on in JCC as well. The very first one is actually very new. It's 1 month old. It was presented in ISSCC 2023. So I start with that. The idea is to go over them, look at their solution, and then really have a discussion of what type of problems we usually face when we're developing these radios. Some of them are full-blown SoC. In other words, they literally do the, let's say FIRA compatible, packet, the modulation as well. Some of them are more targeted to a specific, application. I think the last one is like that. All right, so just some very, kind of general basic considerations for the receiver as an example. Obviously, you have to have some sort of LNA, some sort of gain. This could be voltage to current conversion with some gain associated to it. We do IQ, demodulation, so the mixers come into place. Then we do low pass filtering. Depends on what type of attenuation we need. We might increase the filter filter order as well. So we might have a couple of them in cascade. We might need to do some DC offset cancellation as well. Eventually, the filtered baseband signal goes to the ADC, and it reaches the digital baseband to construct the CIRs and such. Now let's look at the requirements to make it clear in terms of type of complexities that we have to deal with. They have to be pretty wide band. In this case, let's say 6.5 to 9 gigahertz coverage. The signal bandwidth by itself is pretty wide band. It's about 500 to 1 gigahertz. So in other words, the carrier frequency associated to this upcoming signal can vary. The center point of this, this spectrum can vary from 6.5 to 9 gigahertz. So you can see how wide of the matching, for example, we have to deal with, how wide of the noise figure requirement we have to deal with. On top of that, the bandwidth of this this spectrum that sits around this carrier frequency is pretty large as well, about 500 to 1 gigahertz. We need to have a couple of them, maybe, or have 3D AOA, angle of arrival, or phase difference of arrival measurement. You can see in open air ecosystem, everywhere we have Wi-Fi. Wi-Fi is very close to this. As a matter of fact, there are channels of the Wi-Fi 6 and 7 that are kind of even overlapping with UWB today. So there is a lot of pressure on linearity requirement of this system. And then on top of that, we have other blockers as well. So LTE is one good example of it. No harmonics of LTE can fall into our band, or this ITS intelligent transportation system. They also, they can also fall in band, and this is very critical when we deal with the automated, for example. We want to have very low power consumption. Obviously, that's always a requirement, especially if we deal with the coin cell battery, and you can see all the conflicting requirements that are popping up, right? You want to have low power, but then you have to have a very good noise figure because you deal with a very low sensitivity requirement. And then on top of that, you're dealing with a lot of blockers that are coming. So I guess the last sentence that I have here is capable of handling strong reflections in band and out of band blockers with detecting a weak first pass signal. Now let's look at front end. What could be examples of a front end? So to the left, you can see it's inductively tuned NMOS LNA with resistive feedback. So matching is done with this resistive feedback, and then the output, you have some sort of tuned circuit to give you some sort of selectivity, if you will. It's pretty wideband, assuming that the input matching is happening based on this resistor feedback getting shown to the input and some sort of matching requirement for that. But it could be very low Q, so it could be kind of wideband. So if you count the passive components, usually silicon cost comes with the passives. So if you have more passives, it means more area, more cost. So it has two inductors. So it's not, it takes some area, but let's see what are other cases. The middle one is our usual source degenerative LNA. It has a very good noise figure. Linearity, not as good. Obviously, you get Q amplification across the VGS, and that's directly impacting the linearity. And matching is not necessarily wide as well. So it's kind of, it's a good LNA for narrow band, but for a technology that's supposed to work from 6 to 9 gigahertz, maybe it's not the best. And it has 3 inductors. How about the very last one? It's just one inverter, right? So you just put one inverter, you do matching with the feedback, and you put some sort of matching at the input as well. Doesn't look bad. It only has one large component, inductor at the input. Matching is done pretty widely, but then linearity is not probably the best, right? You don't really have any selectivity, if you will. So if we go back to this, you can see how we have to juggle among all the, I think Professor Razavi has a very interesting triangle in one of his books, that we are always trying to chase or trade noise with linearity with power, right? We're really looking, circling around this and trying to optimize and come with compromise, right? So this is a very good example of it. Now let's look at the transmitter and let's see what we can do in the transmitter. The one to the left is IQ transmitter. So it's a Cartesian. So you literally create INQ to go to each of the point of modulations. You upconvert it, and then you transmit through the PA. The one to the right is called RF DAC or DRAC, and I think it stands for digital to RF amplitude converter, kind of polar, if you will. But it's not like a usual polar. Usual polar happens, for amplitude modulation. Actually, it is polar as well, because you are modulating the frequency of LO, and then you have the amplitude. So you have the phase through the LO, through the synthesizer, so LO generation, and you have the raw or amplitude through the RF DAC on top. And now let's see what the requirements are. High output peak power. We're dealing about maximum 0 dBm at 50 megahertz EIRP. But what dictates the maximum power eventually is the application loss. Usually we have to deal with a lot of loss through the PCB, or antennas are not good and such. So our PA ends up to have very high output power. So again, we have to have good linearity because of in-band and out-of-band emission requirements. Again, the thing is that we can't blast the power of the PA for in-band. So we have to respect the in-band FCC requirement with that minus 41.3 dBm per megahertz requirement as well. So that's another pressure on the PA design. And it's pretty wideband. I think I had in my mind to put it here. We are dealing with a very wideband signal as well, 500 to 1 gigahertz. The same wideband requirements, or I would say difficulty that we deal with RX, we have to deal with it in TX in some other ways. Now let's see what the first example of our papers that we're reviewing is doing about it. It's a full-blown UWB SoC. They have 1, 2, 3 RXs, and they have 1, 2 TXs. And the front end is very configurable. You can have all different antennas, or you can see an example of what can be antenna on the cell phone. You can have patch antennas, up to 4 of them, let's say, and you can have this exposed antenna or meta antenna to the side. And based on whatever requirements or whatever application you're targeting, you can have this configurability for your front end. And then they have a lot of digital processing requirements on top of power management and memory management, and they have some GPADC as well. So you can see it's a very full-blown solution. But let's go under the hood and see what they have done for their RX. You can see, so it's an IQ receiver, LNA comes into the mixer, some sort of DC offset cancellation, and 2 level of filtering, some gain, and eventually gets to the ADC. Let's see type of measurements for the noise figure they have. For 2 of the channels, channel 9 is 8 gigahertz, channel 5 is 6.5 gigahertz. It's pretty good. So they're getting almost close to 3 dB noise figure for such a large bandwidth across, let's say, 250 megahertz of baseband frequency. Their RX sensitivity, again, for these 2 different channels, or these 2 different channels, but based on enabling. So if I come back, you can have dedicated RX, or you can have this TR switch included to use one antenna for both TX and RX. Obviously, it comes with the penalty, right? So if you don't use the DPD switch, you definitely have a better sensitivity. You can go higher. You can achieve, let's say, minus 96 dBm of sensitivity. And obviously, if you enable that switch, it drops by about 1.2, 1.3 dB. you can see level of sensitivities that we deal with, like minus 96 dB, minus 96 dBm. And they have similar measurements for the channel 5 as well. Now let's look at their transmitter. All right. So I might need to speed up a little, but whatever is left over, the references to the paper will be provided. If you guys want to look at it offline, please feel free to do so. So their transmitter is direct up conversion. The data, the digital data comes in. They have some sort of non-uniform ADC sampling, which is actually interesting. So they do some de-emphasis or some nonlinearity assertion before hitting the DAG, not ADC, DAG. And they have some interesting explanation of why they do it. And by doing that, they actually improve the mask, because they shape their pulse such that it becomes narrower to the side, although it doesn't lose a lot of bandwidth. And here you can see all different mask requirements. For example, FCC is sitting somewhere here. It's flat, but Japan has much more stringent requirement for their mask. And you can see like here, around here is where, minus 70 dBm, mark. For example, here it's a little marginal. So all these different mask requirements come into play as well. So these are the products that get sold across the globe. We have to respect a lot of different regulatory requirements as well. This transmitter is capable of transmitting about 14 dBm of output power, and you can see the shape of their mask. Let's go to the next example. Oh, by the way, I have some data on on their chip size and technology, which is directly copied from their paper. Okay, so this next example of the UDLB chip is also a kind of SoC solution. It's not as elaborated as the first example, but they also have, in this case, they have 3 receivers and they have 1 transmitter that they can connect to each of these antennas that they want. Obviously, for doing the PDOA or angle of arrival measurement. They come actually with 2 chip solutions. So their front end is sitting in a different technology. So it's actually 130 nanometer SOI, which I believe it's RF-SOI process. And then the rest of their radio is sitting within a 40 nanometer CMOS process with all the digital digital baseband within that project. So it's like 2 chip solution under 1 system in a package. In their RX side, so first slide, first paper didn't have a lot of details on the LNA, but in this second paper, you can see how they're doing their LNA design. I think there is a typo here. This shouldn't be. I just copied from their paper, but I think there's a typo here. Or I don't know, maybe they are dequeuing. Maybe this is to dequeue the inductor as well. It could be actually for dequeuing the inductor to kill the gain, LNA gain. All right, so you can see they're using feedback resistor to do the matching, and they have some couple of components here. They have the TR switch as well, and frequency coverage in this particular chip is 6.5 to 10 gigahertz. They have a very large gain. Obviously, you need to have a very large gain to deal with a very low level sensitivity requirement. For example, here they're dealing with minus 99 dBm level, but really depends on the type of data rate as well. So in this case, they're dealing with the data rate of, let's say, below 1 megahertz, and obviously that helps with the sensitivity being much lower. They have some blocker. So this is with the blocker. So if you have blocker, you can see the sensitivity drops. And this is like for they are at 10%, I think. I don't know if they, it's 10%. Bit error rate. You can define it at 1% as well. Depends on your application. So their TX is actually it's not. It looks like a RF DAC type of transmitter, but it is not. The DSP part, there are a lot of details here, but I don't need to go over all of it. But the basic concept of the DSP is that they use these 3 different pulses to construct whatever pulse they want. And these 3 pulses are equivalent of 8 bits of DAC, and they just walk and they just shift it through a bunch of these shift registers to reach to the DAC. So it is really a DAC that is combining all these 3 pulses to construct the ultimate pulse. And that is nice because you can just fill up this lookup table with whatever shape of pulse you want. So it is versatile from that perspective. But you can see that eventually it comes to a current DAC and it goes to gets up converted through this up converting mixer and goes to the PA. So it falls in direct up conversion type of transmitter, and the transmitter is just single I. There is no I or IQ transmission. Again, you can see some measurements in their power spectrum, and the FCC requirement is shown here. This channel 7 as a definition for channel 7 is 1 gigahertz wide band. So they could actually have a 1 gigahertz band as well. So the last paper I wanted to go over is another interesting one. It is a polar transmitter, and I try to get through it. So they have their injected like ring oscillator, but it is really clocked at very high frequency. So phase noise requirement gets a lot relaxed. And it gets mixed within this digital PA. And the way that they mix it, so the data comes, so amplitude data comes from this pass and phase comes from this pass. And then they get mixed in the digital PA. So the way this pulse shaper works is that they have just a trace of delays. So they have this programmable delay that they basically fit it with this single pulse. And this single pulse gets eventually added to the PAS slices. And this is a RF DAC, so you can just have whatever the slices of the DAC you want and do this mixing of this data, incoming data and LO frequency with these ANDs that you have here. But what is interesting about this is that it is just what do they call it? Just a stack of delays, and you just walk a pulse through it, and you construct this pulse shape, just like that. But then to calibrate, and it has to be very nicely timed, right? Because it comes from the pulse requirement. But then if they want to calibrate this, they make it a ring oscillator. So you can see that this becomes eventually a ring oscillator by enabling this calibration control bit. And they make the frequency of this ring oscillator such that, let's say if it is 500 megahertz case or 1 gigahertz case, they play with this current DACs that goes to the delay element. By playing with those, they calibrate this ring oscillator to be exactly whatever frequency the pulse should look like. And then they open it. And the assumption is that during the transmission of the pulse, temperature hopefully stays the same. It doesn't really vary as much. So you can basically have this very simple pulse shaper, if you will, to construct this shape, right? And then eventually it gets modulated with the RF frequency that is coming from, from this PLL that they have, and it is injected like, so it's very low power. And it eventually gets out to the combiner at the output and goes to the antenna. This paper doesn't have RX, they just have transmitter, and they have some mask measurements in this slide that I put in. This one is for channel 5, and you can see side lobe measurements that they have. It's about 32 dB dBr suppression, and then for channel 9, which is 8 gigahertz, you can see that as well. But again, keep in mind that all these mask requirements that you see here as part of regulatory requirement and licensing, all of this has to be respected as well. Like here, this has to be respected. So for ETSI, which is European regulatory body, this could probably become problematic. There are some, this is a very interesting approach to pulse shaping, but it comes with the limitation. It is PVT sensitive, process voltage and temperature sensitive, simply because they do injection lag and they do a delay line, calibrated delay line for the pulse shaping. It only has one pulse shape, basically 2 frequency, but 1 shape, not like the 2 other ones. And obviously there's no, you can say there's no DSP behind the scenes. Everything is really analogish, very hardware driven with no flexibility. And they don't have the high pulse rate measurement. All right, so I'm almost last slide. Sorry, I ate up a little from the question time. Hopefully we can recover. This is just recap of what I had at the very beginning to give a perspective of where we are. So just cut of it is that, in the receiver side, largely dynamic range and high linearity requirement is what we deal with. In the transmit side, all the stringent requirement for emission mask compliance, it comes into play. There are some new techniques of using RF DAC for this very high bandwidth transmitter, but usually the mask requirement is where they lack, because you don't necessarily have enough filtering to get SCLR, ACPR down to the level that FCC or mass requirements are dictating. And we haven't even talked about the accuracy of the clock and phase noise requirement for the carrier and all the reciprocal mixing problems that we will deal, because we are sitting at frequency that, let's say 600, 700, and 100 megahertz away from our carrier frequency. There's a Wi-Fi, and reciprocal mixing will kill us. All that noise gets jammed into the receiver band, and that just kills the all the sensitivity and PR requirements that we have. Noise figure goes to the roof, right? So we have to deal with a lot of far out improvement in our LO phase noise design as well. All right, so that was my last slide, and I have all the references available. Again, I can post the 3 papers that I borrowed a lot of material from through Michela. We can send that out. And also, this slide is a lot borrowed from what I had in RFIC 2022. So if you guys have access to it, you will get a lot of that material as well. So thanks a lot for your attention. That was end of my talk.
Thank you so much, Babak, for the devoted time and the great presentation. So now we will open the floor for questions from the audience. I just have a small question regarding the last paper you mentioned regarding the ring oscillator.
Yes.
Maybe if you, If
Oh,
you can
yes,
go
it'll
to
be good
the,
there. Yep.
yes. Yeah, so basically I can see that when it's enabled, it's using current starving just from one end, right? Like it's current starving it to control the frequency, the oscillation frequency.
That is correct.
What about the phase noise of the RO? Like maybe you mentioned that it has been relaxed. I can check the paper later on, but if you can comment on this.
Yes, sure. That was a question that came to my mind as well, because for the phase noise requirements that radio technologies usually put in place, we don't necessarily go with ring oscillator. It was interesting that they used ring oscillator and then they injected lock. I think the key is that they are using this external PLL. Maybe it has a very good phase noise to begin with because it's off-the-shelf component from AG devices or such. And they create a very high frequency, right? And this is exactly the integer module of what the carrier frequency eventually will be. And by doing that, they get away from the phase noise problem a lot. But ring oscillator by itself is having a lot of phase noise as well. So I think it really depends on what they targeted from their from their system.
Sure, thank you.
But good question.
I also have a quick question. For slide 26, when you were explaining this new architecture, what was the reasoning of that that pulse shaping? I couldn't quite follow, like that the way that they're using this, I guess, that shift registers, what was the reasoning for that?
Sure. So they have this so-called building blocks of the pulse shaping written here where I have my mouse. It's like they call it ternary code. So you have so let's imagine whatever pulse you have, eventually we have to construct a UWB pulse, like impulse radio means UWB pulse. So basically a pulse that, let's say it's 2 nanosecond or 1 nanosecond long, and it has a very specific characteristic. So it has a, it's a peak, goes down, and this is a large peak, like what I had very early on. So let's say this peak here, right? Let's say something like this peak that you have like this pulse, for example, negative pulse that you have here, right? So what they're saying is that to construct such a pulse, and this is just a requirement of the impulse radio, right? You have to have some sort of pulse that eventually occupies about 500 or 1 gigahertz of bandwidth, and that is providing it. But to construct this pulse, they are decomposing this alternate pulse to a summation of 3 pulses, if you will. So let's say you can say their FFT components of the final pulse is using 3 similar pulses. I mean, FFT usually is sinusoidal construction or deconstruction, but in this case, they're claiming that if I have such a pulse like this with this characteristic, if I change their amplitude, so when I'm here, I probably have, I have maybe lower red, a little higher blue, and a little purple. But what they are claiming, and this is a good example actually here. So if you want to construct a pulse that looks like this, you can combine these 3 pulses to construct it, right? So that's their building block of pulse construction. And what they do, how they do it is that these are all codes, right? So they put the code in this lookup table here, and they just spit it out based on a very accurate timing, such that eventually they walk through. So you can see that this is just walking through a delay line and different DAC associated to that digital data spits out, right? So they have like these lookup tables that are in parallel, and they're all like 7 bits output, but the coefficients associated to all of these is coming from this equation that they have to the very right side. So you just, you give, weight of -1 to data S1, sorry, +1 to data, shape of the pulse of S1, -1 and +1 at any given time, right? To construct this final pulse. So they do all of it, but conversion to the analog happens through the DAC eventually.
Okay. So this is still baseband.
Yeah, these are all in baseband. Yes, okay. These are all in baseband, in digital baseband with all these matrices to construct the pulse that they want. Like here they're saying, this is the ideal pulse that they want, but they can construct it by these 3 pulses weighted based on at what time, what value.
And does it have?
They just pass it through the DAC and then it gets up converted. Okay,
does it have a benefit over other architecture or?
It's very simple, right? You can see, look at this. And this was I think it was a university paper. So obviously they don't necessarily need to have a lot of digital processing in their proof of concept. But you can see there are some benefits, right? It's very simple. You literally just add, fill up a lookup table with whatever pulse shape you want, and you just trigger it to get to the transmitter. Versus, this is industry, right? When you come to industry, this is what you get. That's the idea, but you eventually get to the industry, and this is what you get. You have to have, PMU. You have to have a lot of versatility in your pulse generation. So there's a complete engine behind the scene to do the pulse shaping in much different ways. And and all the FCC requirements, right? If you go back to their solution, you can see, for example, here, there are some cases that there are some cases that are not necessarily meeting the FCC mass requirement, right? But for their application, it was just a presentation from, I think from IMEC it was. So they don't necessarily care about it. But if you want to care about it, your pulse shape has to be more complicated than just a lookup table.
Great, thank you so much.
Sure.
Thank you so much, Babak, for your time. And of course, we will keep an eye regarding future advances in UWB technology and future IC conferences.
Thank you very much. My pleasure. Thanks for having me.
So thank you so much for attending, and please stay tuned for future events from our chapter. And thank you so much, Babak, again.
Thanks, Led. Thanks everyone on the call as well. Have a good rest of the day.
Thank you
good
so
night,
much.
Guys.
Thank you.
Bye.
Bye-bye.
Take care. Bye.